Chapter 3 of the covalent compounds builds on some of the ideas that we have been talking about over the last two chapters, and then adds a little bit of something. What does this all mean to us? Why do we bother worrying about these shapes, these compounds? As we saw last chapter, there's a lot of these that have some real-world application with it, and so now we're going to look a little bit more closely at some of the explaining why we see what we see in the real world stuff. First off, we need to look at what is known as Vesper theory. Vesper theory stands for valence shell electron pair repulsion. And it talks about the electron pairs, how we remember our Lewis dot structures, how they are placed around that element or around the symbol, and how that happens is that we understand that electrons are have like charges, and like charges in physics repel, and so those like charges repel each other, and because of that it's going to give us a very significant or actually geometry that is very predictable in many ways. And it's this that becomes that valence shell. That's that outer shell, again, the Lewis dot structure stuff. And they're talking about electron pair repulsion. It's quite humorous, is that every time instead of whisper, I always think of Vesper when it comes to talking about Vesper theory, because the two sound so alike. We're going to have two types of shapes that we're going to look at. The electron geometry, that means we take into account all of the electrons, and then the molecular geometry looks at what the molecule itself, looks like, and if we see what it looks like, it might make us a little bit easier. Now you will also find a chart, and I'm going to reference some things very similar to that on the back of the periodic table that we have for class. And on the back of that, you're going to see electron geometry, EG, and molecular geometry, MG. And we're going to talk about them as regions of space. And we'll explain more why I use the regions of space, but it all comes down to this idea of Vesper theory. So, electron pair geometry is something that, again, we take into account all of the electrons. The ones that are on the back of our periodic table are talking about these. These are the ones that we talk about on the back of our periodic table. We don't want to deal with, it's not that we don't want to deal with the trigonal bipyramidal or the octahedral, but those are ones that they've expanded beyond their 8, because 2 times 5 would be 10, and 2 times 6 would be 12. And the purpose of this class is not to kind of try to confuse you any more than we normally do in chemistry, but to kind of give you some of the very simple ones. And I think the linear, trigonal, planar, and tetrahedral they're very good. So if we find and are able to identify how many different pairs there are, we'll see how many that. What geometry, and we'll look at some of those geometries as we continue through. Now the molecular geometry, it depends on a couple different things. Is that we have to identify not just whether or not the electrons are actually bonding, but or how many pairs there are, but we also have to know which ones are bonding. So we have to be able to identify our bonds. And that's why it's really nice for us to use those line structures that we had been using for the last couple chapters, instead of always using the dots. If we use the lines, it makes our life a lot easier, and that's what we're here for, to identify those bonding pairs. And so when we look at this, we'll see that if you have 2 electron pairs, you're going to have a linear. Doesn't matter how it looks. However, if you have 3 electron pairs, that would be 6 dots, pairs around paired dots. So you would have 3 pairs around it, you would see that if all of them are bonding, so you'd see 3 lines protruding out, that would be a trigonal planar. That means they're in a plane of the board, so to speak, such as the X or the Y or the Z axes. Now, if it has a non-bonding pair in it, meaning that only 2 of the 3 are actually bonding, then you have what's called an angular or bent. And either of those words are for the most part, pretty acceptable universally across the board. And if you have only one, that means it is linear. The one that you're going to see the majority and spend a lot of the time on, actually, is you're going to see a lot of them come in this region here, and that is you're going to look at, because you're going to have a lot of pairs, because everybody wants 8 electrons, and therefore you're going to see 8 electron pairs quite often. Or not 8 electron pairs, but 8 electrons, 4 electron pairs. And therefore a lot of the geometries that you're going to be looking at are going to come from this region that we're looking at. And therefore you're going to see a lot of them in this block here of the, is it going to be tetrahedral, trigonal, pyramidal, or trigonal, angular or bent, and or linear as they look at. The other ones, again, the trigonal, bipyramidal, and the octahedral, are there for more of a reference. Again, I'm not going to focus a lot of time on them as we continue through. So we have the, how does Vesper theory help predict the shapes of molecules? Well, it takes us through this little step-by-step process where we see a little bit of a Lewis dot structure, and it kind of transitions us into what are known as the line structure. And these little triangles are kind of ways to identify how it's coming out at us. Make it a little bigger there. Actually, maybe we'll make it black there. So it's protruding out at us and or going away from us, as we can see with those lines there. There are other alternative ways in which these could be drawn, but this is just an artistic depiction. Now, this leads us to understand what we have here. And those should make a lot more sense now when we're looking at our molecular models that you've been dealing with over the last once in every chapter of what those shapes actually are. Instead, you haven't been asked what the shapes are, or even what the bond angles are. Now, if you actually took a protractor to our molecular model sets, you would actually see that it's somewhere between 109 and 110. And even more specifically, 109.5 ends up being what it is for all tetrahedral ones. And when I say that tetrahedral, that's identifying the electron geometry and the molecular geometry for those items, or for those molecules. We then have to kind of go through and identify some other things, and the bond angle will change. A linear molecule will not be how do I want to say it? It will not be a 109.5. It will be a 180 because it's a line. It's not going to be that. There's going to be other ones that are going to be the same. So there's going to be little changes in them. So they're going to look like it. And that's why building the models is so important. So you are able to see what they look like as you move forward. So let's try a few out. So we'll try the first one here, and we'll try to stick with using some of the similar colors that we have. And we'll use green for our chlorine, and then we will go yellow for my hydrogen, because that's the ones I have, and white doesn't show up very well with that. So I'm going to draw my chlorine here, and I'm going to see, nope, that's the wrong color. Cl, and then I'm going to draw my dots in here. And I know I'm going to have that one bond with my hydrogen, like I see there, although that isn't probably done up real nice. And so we see that I have this one bond. Well, I have 4 pairs, because remember, one line, one line equals 2 dots. Not very big there, that's for sure. But it equals 2 dots. Maybe I can get that bigger. Yeah, it's 2 dots, and those dots can be bigger than 2. Easier to identify. Well, I have 4 regions then. Therefore, I have my tetrahedral electron geometry. Now, if I look on the back of my periodic table, I'll see that I have 4 regions. One of them is bonding. That means there are 3 non-bonding regions. And that makes this linear. And that does say linear. It's not written out very nicely. But it is linear for my geometry. If I built this, we would actually see that it does actually form a nice 180-degree angle. Now the next one we're going to do water. And that's a good one there, dealing with water. Let's just do it there, nice red there. And so I have oxygen, and then if I take what I know from my Lewis dot structures, that didn't show up very well. We have that, and then my lines at those points, hydrogen, and my hydrogen. I can see again, I have 4 regions around there, because I would have a total of 8 dots around it, and therefore I have tetrahedral. But water is not linear. I have 2 bonds, so it's like 50%. 2 bonds, 2 non-bonding, and that makes it angular or bent. This is the preferred drawing for water. I've seen a lot of students in years past try to draw water very much like this. I consider that wrong, because that looks linear. Water is not linear. Water is bent. Because water is bent, you are alive. That's what keeps you alive. So, next one, after getting on my little rant there, we'll have carbon, because carbon's always going to be my central atom. Oop, not in green, that's for sure. Get rid of a few of these guys here. Get in my way. Got a little carbon here. I'm going to have 4 bonds, because I got 4 things. I'm going to put a hydrogen here, and now I need to start drawing them what's called symmetric. Now same sides. Now a lot of people, when they do the sides and symmetry, they think same side would be up and down, left and right. But actually the same side is kind of actually more of a drawing it, or cutting the atom in half that way, where I see now I have my hydrogen on one side and my chlorine on the other side with that. And here I can see I have my tetrahedral shape again because I have 4 regions, so I have a tetrahedral. And this time I also again have a tetrahedral molecular geometry. So we also have a tetrahedral geometry. The next example we have is ammonia. By the way, that was carbon. That was dichloromethane. The next one we have is ammonia. And we have my N. I'm going to put my non-bonding pairs on top because I know I have to put my hydrogen here. Now I have a tendency of drawing these according to the actual shape that their molecular shapes are going to look like. And that's just out of habit that I have. Now, sometimes my habits are bad, just like you have bad habits. Sometimes my habits are good. In this case, that would be a good one. But it is okay sometimes to draw your nitrogen out similar to that, where it would look more like a T. I'm just drawing it in a way so that we can actually see how this kind of goes together as it moves forward, as we move forward with it. Here we again have 4 regions, each of the bonding ones and the non-bonding pair on top. And there we have a tetrahedral. Again, it's like the same thing all the time. However, we also have, it's different. We only have 3 bonding, 1 non-bonding region. And that ends up being a trigonal pyramidal. And so you have a little bit of differences there. If you build it, you will actually see, again, you got to see that that's what it looks like as you have that little bit of a pyramid. You would think that it would be planar, but it's not. The bonding, this little bonding guys up here, they push these guys down. They don't like them. They repel them. They're like, go away. And so that gives it that bump. It looks like it's up, but it's actually being pushed down to push the non-bonding pairs that you can't see in the molecule when you build it, but they are there. Get rid of some of these, and then we'll do the last one, boron trifluoride. I'll just go with a different color. What should I color use? There's purple for boron. Don't get to use purple very often. And fluorine will go with fluorine will be green again. Maybe you'll just change the color of the green. That'll be fun. So boron is going to be B. I'm going to have 3. Now, where you put these 3, how you put these 3, that's going to come doesn't actually really matter. I'm going to put them at what I can roughly guess is to be about 120 degrees because that's what it actually is. I'll put my fluorine there. Fluorine there. Don't forget to put my other dots around it because they are there. They are important. They might not have anything to do with our structure because we only look at the central atom with that. But it does have an effect overall on a lot of different things. And so here, I only have 3 regions. This is one of the ones that's very few that you have a trigonal planar. And then the molecular geometry, because all of those are bonded, you also have a trigonal planar compound. And so this one, again, this one is, we don't have a molecular model to help us out identify this. However, we do have some of the things that should help us get to that when we start looking at some other stuff. But it does have some of those. We can see them all there. They do work. But what about multiple bonds? Well, multiple bonds is the reason why we call those bonding regions just regions in there. So far, we've only dealt with ones that have single bonds. So when we're dealing with these double bonds, we need to identify and be able to look at which ones are doing with what. So for here, we need to actually see what I'm dealing with is that we have multiple bonds in a molecule. That can happen. Double bonds, as an example. Down here, we've seen double bonds when we've built them in our molecular model sets. And so what we do then is that we have to identify, well, how do we deal with that? Well, it's best to go with, we're going to treat them as just a single bond. Or actually, I prefer a single region. I'll change that here. So we're going to have that single region, and so it's going to, so we don't get confused on whether it's a double bond or a triple bond. It's just a single region, and we just so happen to say it's a region of space that just so happens to be a double bond instead, so we don't have to confuse where that comes from. Instead, it's just a region of bonding. It just so happens that it's a double bond, or it happens to be a single bond, or even a triple bond, as we can look at. So let's look at a few of those. And when we look at these, again, we're going through and trying to identify some of these bonds as we look at them. Carbon is always my central atom. I'm going to start it a little bit at the top here so I don't get too crowded. I'm going to have my oxygen on each side here. You've built this one before, so it should come at no surprise on what it looks like. Now I'm still going to draw my other dots around oxygen because they do have an effect on things. But what I see here is that I have only two regions. I have one region, two regions. They just so happen to be double bonds, but it just also is just a region of bonding. So two regions, if I look on the back of my periodic table, means that my electron geometry is linear, and my molecular geometry is linear. Yay, it makes sense. And now when we get to the next one, which would be, I believe, ethene, we see that we have, again, we have carbons, when in doubt, bond them together. I don't have enough hydrogen to spread them out equally. Well, that means we have a double bond. Yay, since we're talking about double bonds, it should make sense. And I'm going to draw my bonds coming off at appropriate angles as best that I can. And we'll see that we have a little bit, almost a 120 degree angle here. And when I look at it, it does not matter which carbon I look at. I need to look at one of these carbons is how we do it. And that means these other hydrogen not that they're not important, but I'm only going to kind of really identify that region that I have circled in gray there. Only this one's inside there. So this is the carbon I'm looking at. And so I will have three regions. One of them happens to be a double bond. No big deal. But I just have three regions. That means it's a trigonal planar. And if I look on my back of my periodic table, I'll also see that it's also trigonal planar for my molecular geometry. Usually, we don't have too many cases where the electron geometry and molecular geometries don't match up when we look at this. When I see the next one, this one's actual name is acetylene. It's got a triple bond. It's quite energetic. A little bond there, running out of room again. Sorry, I write big. And so we have a little bit of the there. And so what now, again, doesn't matter which carbon I look at, so I'm going to change which carbon I'm looking at. I'm only going to worry about this carbon right there. And so here I have two regions. One of them goes to, well, probably didn't make a big enough circle, but one of them goes to this hydrogen, the other one goes to the triple bond carbon. And so I have another one where it is just linear and linear. And if I build it, you will see that it becomes a linear molecule. Vesper theory enables predictions of three-dimensional molecular shapes because the valence electron pairs. So, what does this mean to us? Well, it adds a little bit of something to it called polarity. Non-polar bonds versus polar bonds. What does this mean for us here? Well, what we're looking for it as is whether or not we're talking about whether or not something can pull more than the other. And that's why when I talk about non-polar bonds, I'm talking usually about non-polars. And that did not right is what there. So non-polars, no one's pulling any harder than the others. Bonds are shared equally. Everything's nice and shared equally. And a polar bond means that you have a polar. Someone gets whatever the item is just a little bit more than the other person. And if you've ever had to share anything, some of us have had to share things in our life. Say maybe you had to share a car with an older sibling. And if you have to share a car with an older sibling, you will see that it's not always shared equally. And it's the same way with the electrons. They might think it's shared equally because they get it more often than you do, but it's not. And so therefore you have a little bit more of a, oh, hey, wait a second, I need the car today. Well, I'm sorry, I need it more. And that's kind of what you can kind of think of when it comes to the electrons. You're like, well, I need the electrons. Well, I need it more than you do, so I'm going to keep it. That's a way to think about it, is that not everyone shares really equally, and so that's where you get these polars. Another way to think about it is talking about these trying to share the electrons is kind of a tug-of-war match. If both sides are equally matched in strength, the non-polar bond, what happened? The middle of the rope doesn't move. Whereas in a polar bond, the middle of the tug-of-war rope moves to the side that is pulling harder, meaning the electrons are going to be pulled closer to them. Here we talk about it as the electron density is pulled that way, but in all reality, that's what you're looking at, is such as the tug-of-war that is happening for these electrons. Now, nothing is giving or taking. One just pulls harder than the other, and that's what happens. So, how do we determine? How do we know? How do we become in the know? How do we know when this happens? How do we know that this works? Well, we have to consider things. The polarity of the bonds is one way of doing it, and you can look a lot of that information up. I don't subscribe to that train of thought. I say look at the molecule shape. That's why you've been practicing them a lot. So you've seen a lot. Draw them out correctly. That's why you've been asked to draw them out a lot. And from there, I think it's very, very, very important to be able to, if you draw them out, you make them, well, you should be able to get, and a lot of times for me, what it actually looks like. You'll actually get the polarity correct usually. Now, every now and then, you're going to get some that are, oh, that one's just a little bit close, or that one's just a little bit off, or, and those things happen. But you know what? A lot of times, it's going to be impressive to people that you know how to get that without having to look up certain values. And you're going to get pretty close. And that's the important part. And sometimes it's not always about getting it right every single time. If you can get yourself close and get yourself on the right track, that's going to get you working. And for my class and for what we're doing here, that's all you're looking to do is just get the answer to where you should have. Now again, for my class, that's going to be the right answer. For other things, you might actually have to look up some of these things, and that happens. So, if the molecule contains all nonpolar bonds, polar's nonpolar. The molecule is nonpolar. It's just how it is. It means the tug-of-war match is perfect. If the molecule is symmetric about the central atom, meaning everything's the same, it's nonpolar. But once you replace one of those atoms with something that's completely different, I would consider that to be looked at as that is going to be a polar molecule because you got that one thing that is going to be different. And that's what happens is that because that one thing is different, it pulls things differently, and therefore you're going to have that tug-of-war match unequal anymore, and so therefore someone's going to win it. And so you're going to have that polar molecule. So again, we kind of looked at this when we were drawing out this dichloromethane, is that we can see the same side stuff. And we look with this same side. We can see that the hydrogen are on one side and the chlorine are on the other. Whereas on this one, you would guess a lot of times, by if I split it in half, oh look, the chlorine are pulling equally as hard on it, and the hydrogen are pulling equally as hard on it. And they're opposite of each other, and therefore they're pulling equally in different directions. That's not the way. In all reality, what would end up happening is the chlorine would pull a lot harder on the hydrogen than the hydrogen can, and therefore they're going to pull the electrons closer to them, and it's going to be a tug-of-war match. And if this were the case, actually what could happen is that the electron densities would probably be more of like a oval or an ellipse, where the hydrogen are going to be pulled down closer to the chlorine. In my mind, that's how that would work. But this is the proper way to draw it. That's why that's the way I'd show you, is because that's the way this should be drawn. Choose the correct words for the spaces. Hydrocarbons are highly soluble in blank solvents because they are blank molecules. Remember the age-old term, like dissolves like. So, let's do a couple more of these things. I love doing examples. And we got our electron geometry, our molecular geometry, and let's go polar. Yes or no? And so we have methane. So we have methane here. I'm going to draw my carbon. I got to draw my hydrogen as well. Okay, draw my hydrogen in here. I better put my bonds in. Now this should be pretty straightforward. That, hey, look, I have a tetrahedral, 4 regions, electron geometry. My molecular geometry is also tetrahedral. Now, whether or not it's polar, well, I would say No, it is not polar because, or I would say non-polar, because all the hydrogen, it's symmetric, perfectly symmetric, perfect 109.5 degree angles, and therefore you're going to have a non-polar molecule. All the hydrogen are pulling equally. How that all works is that it is a non-polar bond. Now, water, we'll draw that. I'm going to draw it a little bit differently to save some space. But I'm going to have everything in the right place still. I'm going to put my non-bonding electrons there. They're definitely going to be important here. And so I see that my electron geometry, again, tetrahedral. Now, the molecular geometry, though, is bent. Notice how I drew it. It looks bent. Now, polar? Yes, definitely. Water is polar. You will be asked on your test for this unit on water. I'm pretty sure. Guarantee it almost. On whether water is polar or not. It is polar. Trust me. We would not put salt on our roads in the wintertime if water was not polar, because like dissolves like. Salt isn't a polar molecule, but polar molecules will dissolve ionic compounds, which we'll talk about next unit. But water is polar. I wish this thing had a video camera. I'd be pounding on the desk. The water is polar. Maybe you can hear it. Water is polar. Hopefully you got that in. So water's polar, if you didn't hear. And it's important. And it's a very important thing. It's what allows a lot of life to happen with that. And if you draw it out correctly, it makes it a lot easier to see it. So then we have carbon dioxide. We got oxygen here. There. See those non-bonding electrons. Yay! When I look at my geometry again, I'm not looking at the oxygen. I'm looking at my central atom. My central atom in this case is carbon. And therefore, I have two regions. It's linear and linear. And some of you are like, but you have two double bonds. That's 4 regions. No, remember, you have regions of space. They just so happen to be double bonds, but they're still just regions. And therefore, they are linear. And now, is it polar? Well, those oxygen atoms are going to be tugging with each other, and that's not going to move the electron density anyway, so you have a non-polar molecule. And the last one is another kind of interesting one, is that we have a ammonia. It's very nice. Put it on our fields, especially if in some cases some people don't. Some people use the all natural stuff. Instead, some people need to add a little bit more nitrogen to the ground, and it's because of this is why we have that smell every now and then in the spring when people add a little bit of ammonia to the ground, spraying the fields with a little bit of ammonia. Now, the electron geometry of this is going to be tetrahedral. Because I have 4 regions. Now it's going to be trigonal pyramid, or pyramidal, or trigonal pyramidal, whatever. So it's going to be trigonal pyramid. And we're going to see that it is definitely going to be a polar. We put it on our fields. The only way it's going to get in the ground is by, well, dissolving into the ground. It's like putting oil. It's not going to go anywhere. It's just going to stay there. It's going to be gross. Instead, the polar aspect of it allows it to go in. That's why it seeps into the soil. That's why it is able to help our plants grow and add that nitrogen to it. So, how do we know which ones will be closer to? It's an idea that we talked about at the end of the previous unit, and that is talking about electronegativity. And that's going to affect on how close those valence electrons are to the nucleus. They're going to pull harder. If we remember back that the trend means that it increases for electronegativity, it increases as you go up, and it also increases as you go from left to right. So some would think that the noble gases are the most electronegative. Well, they don't have an electronegativity. They have full valence shells. What would they care? They don't need to add any more electrons. Instead, fluorine is the greatest electronegative element on the periodic table. It has an electronegativity value of 4 if you wanted to look it up. And it decreases as you go down and as you go from right to left. Well, it also increases when you go from left to right and then from bottom to top. However you want to memorize it, doesn't matter. Well, you should have had it memorized from the last unit too, but that's why we revisit things. So, the first one we talked about is the sodium and chlorine, sodium chloride happening. Sodium and chlorine, they're happening with their, sodium and chlorine are happening with their ions. They're gaining and losing, and so they are changing. This is gaining and losing, and that's why we see that positive, and one has the negative with that as well. And lost my train of thought there. Wow. What we have on the other one is this hydrogen and fluorine. Well, that's they're sharing, but fluorine's not a very good sharer. It wants to have it. And what we see here is with these little sigmas, kind of always looks like eighth notes with the open eighth note kind of a thing. Going with it is that it's a partial charge. This doesn't have a full charge. It hasn't gained and it hasn't lost. It's just partially more fluorines than hydrogens. It's getting back to that car scenario. It's really mine, but it's just partially yours. Is what you can kind of see or view it from. Is that the electron is just, and we're just identifying it, and it's just a way to identify who is the person not sharing well. In this case, it's fluorine. And we also have to identify the other one, and that would be hydrogen. So the one that pulls more harder gets the partial negative. The one that doesn't have it or doesn't pull as hard as the other one is a partial positive. And so that's how that is. Most polar bonds will have that. And so it's just an identification. We're not going to spend an extreme amount of time looking at which ones are which. It's just going to be kind of a, oh, hey, look, this one's positive. Oh, hey, look, this one's negative. And then kind of go from there. Otherwise, for me, I prefer most high school students to just be able to identify the fact that it's polar is a big step in the right direction. Being able to identify which one is pulling harder than the other, that's just gravy. And that's just kind of what we're looking at. So it's not going to be super crazy if one happens and the other one doesn't happen. And so it's just another way of doing that. So what does this all mean to us? Well, we talked about and had a question about it and looked at like dissolving like. Polar molecules don't mix with non-polar molecules. It's not that they don't like each other. It's just that they just don't interact. They're the electrostatic attraction and like dissolving like just doesn't allow for it to happen. And so they don't mix when they're in liquids. That's actually why oil and water don't mix. It's not the fact that their densities are different. That's why they separate in the way they do. But the fact that they separate is the fact that they're non-polar molecules and polar molecules trying to mix. That's just how it happens. Now, you also would see the same thing. They say the same thing with solids. They don't mix very well as when you look at it. And this actually explains the why when the hero on a movie it jumps into the water that has gasoline on it, dies underneath after it's been lit, and they're perfectly fine. Well, the gasoline stays on the top, and then they just have to go to where the gasoline's not, and they're going to be able to pop up and survive. And that's where that happens. Now, how much it could potentially mix, depending on the sheer amount of it, how it's being mixed up, and some of those types of things. But for the most part, it's not going to be that way at all. They're not going to mix. Again, because you can shake up a bottle of a vinaigrette, and it's going to mix for a certain amount of time. But eventually, it breaks up, and you don't have it happen. They separate out, and you'll never be the wiser on it. And so you have those little separations that will happen. And in gases, they can mix. And it's like, well, why? Well, if you remember back, that gases are really spread out when they're in their at the molecular level. They're very spread out. So sticking to things that are not alike are not unheard of. They can easily be in the same place, and they're going to just be completely so spread out that they can't see each other. Because they can't see each other, there's no reason for them to separate from each other. In a molecule, the atom with the largest electronegativity value when polar molecules are placed between oppositely charged plates, the negative well, there's the end of Unit 4. Next unit, we're talking about ionic compounds, and that's a give and take process. And so it'll be a little bit different on covalent compounds. We've spent a lot of time talking about their how these bonds occur, where we see these bonds at, and not as much time talking about the naming of it, because that's pretty simple stuff. In the next unit, we talk a lot more about the naming and some other things. So we'll talk to you then.